Hey guys, welcome to this video for question 2 and question 3 for the 2019 level 3 mechanics exam. So question 2, we have the merry-go-round. So 3 children are playing on a merry-go-round with a rotational inertia of 271 kilogram meters squared. Once the children get on the merry-go-round spinning, they stand evenly spaced around the outer edge. Each child has a mass of 28 kilograms and the merry-go-round has a radius of 2.1 meters. Question A. Assuming the rotational inertia of a child's mass on the edge of the disc is given by I equals to mr squared, show that the rotational inertia of the system is 641 kilogram meters squared. So the system consists of the rotational inertia of the children, so that we can say that the total rotational inertia, so total rotational inertia is equal to the rotational inertia of the children plus the rotational inertia of the edge of the disc. So we can say it's equals to the rotational, the rotational inertia of the children plus the rotational inertia of the disc. Alright, so we're told that the rotational inertia of the merry-go-round is 271, and we also know that the children's rotational inertia can be calculated using I equals to mr squared. So we can say that the inertia of the children is equal to the total mass of the 3 children, which is 28 times 3 multiplied by the radius squared, which is 2.1 squared. And then we're going to add that on to the rotational inertia of the disc, which is given in the question as 271 kilogram meters squared. Should get an answer of 641, but just to double check. So 28 times 3 times 2.1 squared plus the 271. Yeah, that gives us a rotational inertia of 641.44 kgm squared, and that is equal to 641 kgm meters squared if we round it to 3SF. And this should just be a standard achievable question. Question B. The total energy of the system is 388 joules. Show that the angular velocity of the system is 1.1 radians per second. So the angular velocity, so we want to show that the angular velocity of the system is 1.1 radians per second. Alright, so we have that the rotational energy is equal to 388 joules. We have the total rotational inertia, we'll say it's 641, so we say inertia equals to 641 kgm meter squared. And we also have, no, that's it, that's all we have. So we can use the equation for the rotational kinetic energy, which is given as EK. The rotational energy is given as half IW squared. So in this case, we have the rotational energy is 388 joules, and we have the inertia, the rotational inertia is 641 kilogram meters squared. So we can plug those numbers in and rearrange to find our angular velocity. So we can say that 388 is equal to 1/2 times of 641 times of angular velocity squared. So if we rearrange to find angular velocity, we'll have 388 times 2 divided by 641, and square root will give us our angular velocity. Our angular velocity comes out to be 2 divided by 641 and square root. Yeah, that gives us an angular velocity of 1.1 radians per second. And we have to show that the linear velocity of one of the children is 2.31 meters per second. So in this case, now we have the angular velocity of the system is 1.1 radians per second, and we also have energy equals 388 joules, and we have inertia equals 641 kgm squared, and we also have that the radius is equal to 2.1 meters. So in this case, we can use the equation that v is equal to the angular velocity multiplied by the radius. We can say that the linear velocity, so that's the not rotational velocity, but the linear velocity is equal to the rotational velocity times of the radius, so Rw. So that means v, our linear velocity, is equal to 1.1 multiplied by the radius, which is 2.1. 1.1 times 2.1, that gives us a velocity of 2.31 meters per second. Alright, so both of these should be your final answer. So your final answer is here and here. And if you get both of these, that should get you a merit grade for both. To get just one is an achieved by itself. Okay. Question C. One child drags a foot on the ground to bring the merry-go-round to a stop in 2.8 seconds. Calculate the amount of torque produced by the foot. Alright, so looking at our formula sheet, we have a torque equation. Sorry, not my pen. We have a torque equation as torque is given as torque equals to the angular acceleration multiplied by the rotational inertia. So right now we have the rotational inertia as 641 kg meters squared, but we do not know the angular acceleration, which we're going to try to find with the information. So one child drags a foot on the ground to bring the merry-go-round to a stop in 2.8 seconds. So when it says brings it to a stop, that means once it stops, it has an angular velocity of 0 radians per second. So we can say that our final angular velocity is equal to 0 radians per second. Our initial angular velocity was actually 1.1 radians per second, which was from the previous question, and brings it at a stop in 2.8 seconds. So we can say that the time taken for this change was 2.8 seconds, and we're trying to find our angular acceleration. So in this case, we're going to go to your formula sheet, and you're trying to find an equation that has all four of these variables. So the equation that would satisfy for this specific case would be that the final rotational velocity is equal to the initial rotational velocity plus the angular acceleration multiplied by the time. So if we plug our numbers in, we can rearrange the equation to find for our angular acceleration. So our final angular velocity was 0 radians per second. That equals to 1.1 plus of 2.8 times of the angular acceleration. So if we rearrange this, we get negative 1.1 divided by 2.8 is equal to our angular acceleration. So therefore, negative 1.1 divided by 2.8. Our angular acceleration comes out to be negative 0.393 radians per second. Alright, so this negative here in front of the angular acceleration just means that the merry-go-round is slowing down, basically. And the acceleration is in the opposite direction. So now we have our angular acceleration. We can use the torque equals the angular acceleration times rotational inertia. So we have our torque is equal to the angular acceleration, which we can use as a positive because the negative is just representative of the direction. So 0.393 multiplied by the rotational inertia, which is 641. And that gives us a torque of 251.82 Newton meters. This should be your final answer, and getting all the way up to 251.82 Newton meters should get you a merit grade. In terms of getting an achieved grade, finding your angular acceleration here could get you an achieved grade. Question D. The children get the merry-go-round spinning once again at a constant angular speed. Then each child moves inwards towards the center of the merry-go-round. Using the physics principles, explain the effect this has on the rotational energy of the system. So when the children are moving inwards towards the center, that means the center of rotation is now closer to the center of mass of the system, and that also means that the rotational inertia is actually going to decrease, because we know that our we know that our inertia is equal to, inertia equals to mr squared. So as the children get closer towards the center, this radius value is going to go down. So while the mass of the children and the disk is going to stay the same, so therefore our rotational inertia is going to go down. So we're trying to have the effect on the rotational energy of the system. So we know that the kinetic energy for rotational is equal to half times of the rotational inertia and the angular speed squared. We know that the rotational inertia is going to decrease, but we do not know yet what's going to happen to the rotational speed. So we have to use another formula to see what's going to happen to the rotational speed. So we know that when the children are spinning at a constant angular speed, they will also have a angular momentum. Okay, so they're going to have a specific L value. So that L value would be equal to IW. So assuming there's no external torques acting on the system, we're going to assume the conservation of momentum. So once the children move in, the rotational momentum is going to stay the same. However, we know that the rotational inertia is going to decrease while the momentum should stay the same. So that means in return that the angular speed of the system should go up as we established that the angular momentum has stayed the same due to conservation of momentum. So while we have our I value has decreased while our angular speed has increased. So this has increased here. So this can be a pretty tricky one to work with. However, we know that EK is proportional to I, but EK is proportional to angular speed squared. As seen here, we have our EK is only proportional to I. However, we have our EK is proportional to angular speed squared. You can kind of think of it as a way that the angular speed is could be like counted twice, as it's this can be rewritten as angular speed times angular speed. So you can say that this is it's not necessarily counted twice, but you can say that it's been multiplied again twice. So what I'm trying to say is that even though this inertia has decreased, because the angular speed has increased and EK is proportional to angular speed squared, the overall kinetic rotational energy is actually going to have increased. It's increased slightly, okay? So as a result, our EK is actually going to go up. Alright, so now we have to put everything into word form. Alright. So we can say, when the children move towards the center, move towards it's now closer to the center of rotation. Assuming initial momentum is larger. Sorry, not larger, what am I saying? Is the same. Kinetic. Sorry. Alright, so this question, sorry for the long period of silence, but so basically for this question, we say when the children move towards the center of mass is now closer to the center of rotation. I equals to mr squared, and the r value decreases, hence the rotational inertia is going to decrease. Assuming there are no external torques, there's going to be assuming conservation of momentum. And this means that the initial rotational momentum is the same as the final rotational momentum. I forgot to add rotational here. This should be rotational and rotational. And we know that our rotational momentum is equal to our rotational inertia times of our rotational speed. And we know that the rotational inertia has decreased while the momentum has stayed constant. Our inertia is inversely proportional to our speed, meaning that meaning that the rotational velocity will increase. So our kinetic rotational energy is equal to half of I angular speed squared, and we know that I is proportional to EK and EK is proportional to angular speed squared. Angular velocity has increased while I is decreased, but because EK is proportional to angular speed squared and EK is only proportional to I, that means that the total rotational energy will actually increase. So that would be your answer for this question, and the whole thing here that should be able to get you an excellence grade. To get a merit grade, if you can link it up to the rotational velocity increasing, so up to here, that should be enough to get you a merit grade. And to get an achieved grade, if you can establish that the rotational inertia decreases, then that could be enough for an achieved. Alright, question 3, swing. So J is enjoying a swing at the playground. The period of one oscillation is 2.4 seconds, and J maintains a constant amplitude of 0.31 meters by swinging her legs back and forth to replace the energy lost due to friction. The mass of the system, J in the swing, is 70 kilograms. J's motion can be considered a simple harmonic motion. Question A. calculate the maximum velocity of J in the swing. So let's just note down all the variables we have. So we have the period of one oscillation, so our period is equal to 2.4 seconds. We have our amplitude is equal to 0.31 meters, and we have our mass is equal to 70 kilograms. And what we're trying to find the maximum velocity. So for the maximum velocity, we can just say that v is equal to amplitude times of our rotational velocity. That's because at the maximum velocity, it's going to be traveling at the equilibrium point. So when J reaches the equilibrium point, she is going to be traveling at that maximum velocity. So our maximum velocity will be equal to our amplitude times our rotational speed, okay? So we have our amplitude is 0.31 meters, but we do not have our angular speed. We have a formula in the formula sheet that says that our angular speed is equal to 2 pi times the frequency. We know that the frequency is equal to 1 over t, 1 over the period. So therefore, our frequency is equal to 1 over 2.4. So therefore, if we plug 1 over 2.4 into our equation, we'll get that the angular speed is equal to 2 pi over 2.4. And if we plug that into our equation for our maximum velocity, we'll have v equals to 0.31 times of 2 pi over 2.4. And that should get you a maximum velocity of 2 pi over 2.4 times 2.4. That should get you a velocity of 0.81 meters per second. And this one is just an achieved question. Using a reference circle or other method to determine how much time J's displacement is greater than 0.2 meters from equilibrium over one period. So in this question, we're going to be using our reference circle. So we're going to split it into quarters. Sorry, my lines aren't very neat, but we're going to split it into roughly quarters. Alright, so the question asks us for how much time, total time, that J's displacement is greater than 0.2 meters. So let's just say, so basically it's saying for how long is the J is going to have traveling at a height above 0.2 meters, above this equilibrium point. So for example, we draw a rough diagram here. We can say that this point here, maybe, what am I doing? Alright, so let's say we have a rough diagram here. We know that the radius of our reference circle will be our amplitude, which is 0.31 meters. And our height here will be our displacement, which is 0.2 meters. So basically, how long will it take for her to reach here? And how long for her to reach back down to here? So here we're going to have the exact same triangle. So here. So this is 0.31 meters, this is 0.2 meters. So basically we're trying to find this time, and it's going to occur at the bottom as well. So we're going to try to find this time as well. So this time 1 plus time 2. And these two times are going to be the same because these two halves of the circle are symmetrical. Alright, so the easiest way to do this question is to find out what this little part, okay, it's really hard to explain. Sorry, what am I doing? Alright, so the easiest way to approach this question is to find out how long she takes from this point A to this point B and then multiply it by 4. So in order to do this, we can draw another right angle triangle, the exact same. So we can say, in this case, if this is 0.31 meters, but this length here is equal to this length here, so this length here is 0.2 meters. And we're trying to find this angle theta, which is our distance, this radians, okay? So in this case, we're going to be using our cosine, so cos inverse cos of 0.2 divided by 0.31. Remember to set your calculator on radians, so inverse cos of 0.2 over 0.31, and that gives us, oh no, I'm on degrees. So inverse cos of 0.2 divided by 0.31. That gives us 0.87 radians. So this angle here is 0.87 radians. and we can use this angle in the equation of, sorry, what am I doing? Angular speed multiplied by time is equal to our angle theta, which is the 0.87 radians we just found. We already found out that our angular speed was 2 pi over 2.4. So now we can substitute to find the time. So we can say that 2 pi over 2.4 times of the time is equal to 0.87 radians. So 0.87 divided by 2 pi divided by 2.4, 2 pi divided by 2. And that gives us a time of 0.332 seconds. So basically from point A to point B, it will take 0.332 seconds. So because this circles are symmetrical, that means for example, this point is point C. So from point B to point C, it's also going to take 0.332 seconds. And from point A to point C, the displacement is always going to be 0.2 meters above the equilibrium. So this horizontal dotted line is our equilibrium, and for this sector of the circle is always going to be above 0.2 meters before it drops back down, and then it's going to have the exact same triangle here. And from this point, let's say this is point D to point E, the displacement is also going to be above 0.2 meters, and that's the exact same as point A to point C because the circle is symmetrical. So basically, we can just say that because the circle has equal quarters, the total time that there is a 0.2 meter or more displacement above equilibrium will be 0.332 times 4, which is equal to 1.328 seconds. So that's the total amount of time that that J will be above, will be 0.2 or more above the equilibrium. Yeah, I hope that makes sense. It was pretty difficult to explain, but I hope that all made sense in the end. Using this reference circle and the triangles in order to find, using this triangle here in order to find the time it takes from point A to point B. I hope that all made sense, and this question, it should just be a merit level question, and to get an achieved and think